Hello, I am Caesar Hu from Team 5921, the Blockheads. This is a video from the speaker series presented by Mr. Michael McHenry, who is a renowned engineer at JPL.
Thank you all so much for coming out tonight, and I'm Jessica and I'm one of the outreach directors.
I'm Miles, I'm also outreach.
And we would just like to welcome Dr. McHenry and
His presentation.
Yeah.
All right.
Thanks. I wasn't sure of the audience or the expectations. I have a short sort of career brief that was kind of fun. And what I didn't do, which I'll try to go fast so we can do later. Broader context, my career ends here at Jet Propulsion Lab, where I've done lots of things for the Mars rovers. So I don't have a lot of Mars eye candy here about the rovers, but I can talk about it forever. So I'll zip through my career, and at the end I can answer questions about what I think about my career evolution and how I ended up there and what I thought about it, or I can answer questions about Mars rovers. So whatever people want. Not off to a stellar beginning. Miles, so I intended to share the whole screen. Oh, there, that's now it should be able to. All right, thank you. Okay, just to provide some motivation that I was once in high school, thinking about what college to go to. There's some pictures of me doing nerdy things. I'm playing the baritone saxophone in the jazz band. My father was engineer, chemical engineer. He's in the bottom left on the cover of Plastic World magazine. He is in our circles most famous for having largely invented the squeezable ketchup bottle. I can tell you about the sophistication of the machinery that goes into making that. And in fact, I worked 2 summers in the bottling plant that manufactures those. And it was a lot less fascinating than time that he had inventing them, but still fun. I was into chess at a pretty early age, and so that in the middle was a chess computer that I got before such things were commonplace. It was actually, I discovered it mid-November for a Christmas hidden in the closet, and for like a month I would wake up at 2 a.m., sneak in, take it out of the box, carefully unwrap it and play for a few hours, and then put it all back so that I didn't get busted. My father got us a Apple IIe. I realize now this slide is super dating and it makes me seem super old, but it's okay because I kind of am. But he bought us an Apple IIe when such things were not commonplace. He claims it was for my education and so I could get to start programming. In reality, there was a software that taught you how to count cards playing blackjack, and he wanted to and did successfully sort of learn how to count cards well enough to get booted out of at least a couple casinos. The Cadillac is very close to the one we had, and so my father recruited me to help work on the cards, and I am largely a software person, but I do robotics, and so having some comfort level with hardware is essential, and a lot of it came from opening up the hood of that car. The top right, I forgot about this until I just happened to cross it. So there was a self-education kit that basically walked you through basic digital and analog electronics that I think probably around 6th or 7th grade that they gave me to that. And I was not a particularly disciplined kid. I don't know how I got through those, but it certainly sort of set me forward on the path of engineering. So, entering college, I went to Rice University in Houston, Texas. I got a bachelor's in electrical engineering and a master's in electrical engineering. And so I know a lot of you are at the cusp of that transition and probably kind of stressed. I'll say that for me, Rice was a great choice. It was quite small. When I was there, it was only 2,500 undergraduates. It has a kind of unique dorm and college system that puts you in a social environment with about 300 other kids that you stay with throughout the whole 4 years. And it was pretty great. It has relatively small classes, but they really value teaching. So you go to a lot of big schools and you'll find graduate students teaching most labs and classes. That was not the case at Rice, and it was great. I wasn't sure what to think about going to Texas. Culturally, I'm a Midwestern or Easterner, but Houston was just Texas-y enough, in my opinion, so it was a fun experience. Most of the students and the people I hang out with, they weren't actually from Texas. Sort of like when I came here, I felt like I was here for 3 or 4 years before I met any native Californians. The next thing I want to say is classes got more fun each year. So I was an okay high school student. I was not a great freshman and sophomore in engineering in college, but and I think it was largely because I felt like I was just learning other textbook material. I was sort of being slopped learning from a big container, and I was eating it up. But as you got to higher level classes, and I think Rice was particularly good about focusing more on core understanding, and so the tests were not sort of application of one equation or another. They would wrap up what you were supposed to have learned into sort of unique and first-time problems that you had to solve in those tests. And it was challenging, but also a lot of fun. And so as I got to be a junior and a senior, I thought I liked the trend, and I think I wasn't ready to enter the world, so I stayed for another year to do what's called a professional master's or a baby master's, meaning not a thesis, but I did do a independent study, and I was so entertained because I remember vividly, I found this paper, and my advisor had said, why don't you implement this and see if you can make it any better? And I vividly remembered it as being very influential on me, not so much in academia, but when I saw the name again, I realized, I immediately recognized the reason I picked it from the file was it had such a cool name of neocognitron. And it was one of the first, it was neural networks before they were cool. And I'll talk more about how that independent study panned out in landing jobs. The other thing I did, I think all of my internships and summer jobs were interesting, even the ones that were sort of less technical. So I told you I worked in a bottling plant. I actually worked nights, made quality union wages, so I was more flush with spending money than a lot of my peers when I started school. My first real sort of professional programming was actually with the geology department in Fortran, where they had this fancy system for doing seismic surveys and processing, and they had a lot of rock jocks and not a whole lot of software people, so they were very appreciative of the little bit of coding I was able to do in the summer. And then I spent the summer in Columbus, Mississippi, in a plant that makes window lift motors. So not very glorious, but it was super interesting to see sort of manufacturing in mass. And I really worked with a lot of industrial engineers, where people are really focused on maximizing manufacturing efficiency. And when you're down to trying to optimize a process to save a few seconds here or there because you're making such volumes that it translates to a lot of money, it turns into some interesting problems. All right, so one slide of unsolicited pre-college advice. So the social structure matters. So if you're thinking that you're making your choice of where to go strictly based on sort of reputation and panache that you think it has, I strongly encourage you to consider how the social environment fits with your personality. Like I said, Rice was great for me as kind of small and very conducive to introverts, as I was at least at that time. But it also, challenged me by putting me in a culture that was different and super interesting. All right, so the one thing, if you take one thing away as sort of engineering club people about to enter college, it's the second bullet, which is join a research lab, maybe not as a sophomore where you're still sort of getting settled, but as a sophomore and maybe a junior, join a research lab. There's nothing that you will do that will give you more in-depth glimpse of the application of engineering and honestly the fun and creativity of it. My father was adamant that when I was at Rice that I do it, and I never listened to him. I managed to survive, but when I was in grad school, I really saw how much the undergrads in the lab got out of it, and it's super fun. It's obviously challenging to fit in with all of the sort of the homework study and such, but most labs are pretty flexible about how much time you spend in there, and if you're at all interested in grad school, it's very enabling to have something to talk about the project that you worked on. It's very common that the advisor of the lab that you work in as an undergrad with facilitates and writes great recommendation letters, or even sort of hand delivers you to a good graduate program that is part of their sort of network and community. So do that. Other thing I'll say is take eclectic electives. So of the classes that I remember most from my undergraduate days, most of them were not engineering. I remember drawing, I remember architecture for non-architects, I remember some super cool sociology classes. So don't waste the opportunity to take very different and interesting challenges. I don't know how, a lot of schools have pass-fail programs where you can take some of them pass-fail, so they don't necessarily have to be high stress, but I strongly recommend. All right, so lastly, I just want to say, and I might be overgeneralizing for my daughter's level of stress, but I'll just say, it's going to be okay. Everybody ends up loving their college choice. I don't think I've ever met anybody that didn't think the college years were some of the most fun years of their life, so don't fret too much about it. I'm going to describe the rest of my career, and I clearly never had an elaborate, well-defined life plan, and I've had a pretty great career thus far, and so I don't think it's necessary. I think the secret is to challenge yourself in the near term, like take near-term steps that are a little bit outside your comfort zone, and it's okay if they're different and you don't see how they line up with the plan. Things have a weird way of coming together. So my experience early on in getting in some manufacturing and things actually turned out to be enabling later in my path in grad school in ways that I never would have imagined. And then lastly, my father's best advice is nothing illustrates what the right decision is in a particular situation more than making one. So you make a decision, in the worst case, turns out to be a bad decision. There are very few decisions that you can't undo and go back, and oftentimes it's not nearly as frightful as you imagine. All right. So after I finished my master's, I went through the colleges bring in companies and for interview as you get, and I went through the interview circuit. I'll just say in that interview circuit, I signed up for some company that I didn't know very much about. It was called JPL. It was the worst interview I've ever been in on both sides of the table. I hadn't done much research. I barely knew what they did, and JPL is a place, especially the people that go out interviewing, that they're used to talking to people that are passionate about space. They've been thinking about space their whole lives, and that was not me. And within the first 5 minutes of the interview, we both recognized that we were just killing time for the next 20 minutes until our time was up. But it turned out to be okay, and I snuck in again later, as you'll see. I did work at British Petroleum Research, so an oil company. By itself, not very sexy, not necessarily something you think of as high tech. When I was there, it was one of the last sort of research labs, like true research labs, where there was not a strict connection of funding between the research that we were able to do and the business return on investment. So we had relatively free reign, and we could tell them we think it would be super powerful if we could develop this capability, and we had generally free reign to do that. Now that ended not long after I was there, like most such research labs, but it was great. And, in particular, I had a circle of people, advisors effectively, that were sort of AI experts, before it was cool. I get excited about that Lisp machine that I worked on, but unless you are a Lisp nerd, it's hard to describe how cool this was. So I provided a link. It was a symbolics machine. Sometimes you can look in a history book and you can see it on it. It was remarkably cool. Like everything that contemporary IDEs do now for you in terms of completion and syntax and things, it did it, and that was kind of miraculous in the day. Observation is that close up everything is hard, complex, interesting. One of the things I worked on there was a system to train refinery operators, and refineries are actually super interesting, complex feedback systems. And so when you start to see that like some temperature on some tank is going out of bounds, there could be 100 different reasons that that's the case. It could be that the nature of the crude that started getting processed changed. It could be that 4 steps upwards, something else is out of range, and so the chemical composition of the fuel coming through is changed. And so it's super challenging to run safely. I went to some training, simulation training companies, and they were also training nuclear operators at the same place, and it was super good. Something as kind of boring as heat exchanger maintenance optimization. So heat exchanger is pretty obvious. You have a lot of things coming out of the refinery pipeline that are super hot. You have to cool it off before you can do other things. So these big heat exchangers, but the nature of them is they get fouled gradually over time. And so, but in order to take it offline to clean it, basically got to stop the whole refinery. So it's super expensive, like it's millions of dollars a minute that the refinery is shut down. So doing it as little and as effectively as possible is a big cost saving. And so I had this system that helped diagnose and advise you when to do it. And it turned out to be great because when I left there to go to grad school, it was valuable enough and important to them that they paid me as a consultant to sort of maintain it when I was gone. So when I was in grad school, I was making a healthy amount of money working relatively small amount of time as a contractor for British Petroleum when I left. The main thing I got out of the PP experience was the people that I worked with, and in particular, before then, I wasn't that set on grad school, and I wasn't that interested in a PhD, and in part I think it's because I had a very poor understanding of what a PhD was and what it bought you. And so you always hear that a PhD is about you becoming the world's expert in some very narrow niche, and that's kind of true, but in reality I was awestruck that all of the PhDs that I worked with in my research section, they had incredible breadth, and so they could take some new problem that they hadn't heard of, and they could cast it into the theory that they had sort of up and down, and figure out and know just what techniques to apply. And it was very impressive and seemed super empowering, literally. And in the end, I now view PhDs as different. PhDs are sort of like PhDs are sort of like college degrees. It's partly what they teach you, but it's a lot more about the signaling that it says about I'm willing to and have demonstrated that I'm capable of taking a new problem that other people don't know how to solve and studying it and pushing it far enough to sort of make a unique and new contribution to it. And you guys won't appreciate, but as a Southern California renter, I had an apartment in Cleveland that was glorious, and I paid $600 a month for it. It was, I could go on about how beautiful this was and how spacious it was. And my friends thought I was crazy for paying $600 a month, and I had never, not since lived in a place so, not since I came to California, lived in a place so nice. I left BP after 3 years, and I came to grad school at USC, actually in computer science. I did not originally necessarily start thinking about robotics. I was actually more interested in computer vision, and specifically, there was a lot of work going on then at the interface and taking the lessons of biological vision and applying it to computer vision. And that's kind of what I was excited about coming to USC. But I ended up getting a research assistantship in advisor Professor George Becky there, sitting in front of the robots in the red shirt, and he had a project that was about manufacturing and automation. And because I had some of that experience I alluded to earlier with respect to some familiarity with manufacturing from the window motor lift and the bottling plant even, he thought I would be a good person for that. It's unclear if he was right or not, but it gave me my assistantship. Then translated to a little bit of a research project that I think was National Science Foundation on a anthropomorphic robot hand. It's there, and you can't really see it well, but it's there in the foreground on the right. And then I also started doing some user interface work, so some robotic human interfaces with subcontracts from JPL to USC, and I started working on that, and eventually that was the way I snuck into JPL. My actual thesis was about the path planning of a robot manipulator, so a link manipulator like you typically see, and it was interesting, but did not make a particularly big splash in academia, but that was fun. Oh, so besides showing you how nerdly the whole crew was, especially Andy wearing the visor. So I think Andy was sort of a more senior grad student in the lab, and so he was super helpful and really sort of instructed a lot of us. But he probably the biggest thing he taught me was to be unashamed of being a nerd. So he before there was anything like Vision Pro, he would walk around in the mall with this big backpack that had his computer on it and the eye display, and I would just walk 10 feet behind and watch the looks on the people that passed him coming the other way. It was entertaining. But in that robot right in front of Professor Becky, you see, it's just a RC car with this bumper on the front. And Andy was interested in reinforcement learning, so not having to sort of teach the robot exactly what to do, but essentially have it figured out through experience. And so that little car would basically drive around on the floor of the lab, and every time it hit it had some sonar sensors to sense the world. Every time it hit something with one of the bumpers, it would take that as negative reinforcement, and it would change its internal parameters to make it less likely that in the same situation it would do the same thing. You had it hooked up to a speaker, so every time it ran into something with a bumper, the speaker would go, ow! And if it successfully made a small motion and didn't hit anything, it would ring a little bell like a Pavlov bell. Super annoying. So the thing would get caught underneath your desk, and you would, for 5 minutes, ow, ow, ow. But super silly. But that work actually translated to what he's been doing most recently. So that little baby with all the brain sensors on has cerebral palsy, and one of the fascinating things is cerebral palsy has poor muscle control, but he was always interested in brain studies, and there are sort of developmental milestones that your brain has to go through to sort of develop healthily, and a big part of that is being able to get the association between the motor commands you make and what it does to your vestibular system and how it translates to motion. And because, particularly as babies, cerebral palsy kids don't have the same motor control and the same strength, they don't get that feedback at a crucial time in the brain development. So Andy and his team made these basically skateboards for babies. And so basically they lie on this skateboard on their tummy, and it takes the very small motions they make, and it's got robot wheels around it. It basically amplifies the small motions that they make and moves them a lot, so they get the same sort of vestibular response that they would get, and it's shown that it significantly helps with their development. And it's just fun stuff. And basically everybody in the lab had cool, fun projects for grad students. You know, at least my advisor everybody was doing something wildly different. There was one of my cohorts, it had a ginormous life-size plastic horse and was trying to develop a system so that people could learn how to ride a horse sitting on the plastic horse without a real horse. I'm not quite sure why, but it was certainly entertaining. All right, so that user interface work that we were doing for our DARPA project for JPL was eventually my into JPL. So after I graduated, I could no longer work as a research assistant. So I basically made a company of one myself, and I got a USC subcontract to sort of continue the work for USC in turn for JPL. And eventually I ended up contracting directly with JPL, and so I basically was a company of one working for JPL, and it was really nice because you're making big bucks, because if you're a contractor, your hourly rate doesn't reflect your health insurance costs or a lot of other costs. So I was making very, very good money, but it eventually became limiting because as an outsider, I couldn't lead other tasks that I wanted to lead that were sort of other interesting projects and new projects. So I became a regular employee after about 4 or 5 years. So I done a lot of things at JPL. I basically categorize myself as a planning and computer vision application engineer. So I am not a hardcore vision nerd, but I knew enough of them that they could help me get through what I needed to know in order to sort of build new capability. And that made them happy because they were very focused on the very niche vision parts of the problem. But so I started with a vehicle up in the top right, which is called Irby. You see it's got 2 cameras on the front. And so the bread and butter of the lab then, and still, even on the Mars rovers, is this stereo processing. You have a carefully calibrated left and right camera. You match what a certain pixel is seeing in the left camera with where it shows up in the right camera. You have very careful calibration of the two. So basically, you know the angle that that point in the world subtends to both cameras. You do a little bit of trig, and now you know the range to that particular point. We do that across the whole image. So basically, turn the left and right images into a depth image, and now that's what the rover uses to decide where it is and it is not safe to drive. So I largely spent the first 10 years of my career at JPL working on various sort of what we call reimbursable or mostly defense, like DARPA, or I did a bunch of work with the Navy, including some people in San Diego who were working on similar ground robots, but that were more focused on and interested in using robotics for bomb disposal. But I started doing gradually more and more on the flight software side, and so I always tell people I touched 6 lines of code in the Mars exploration rover, so Spirit and Opportunity. And then in Curiosity, I got brought on board to help as they were testing, even after landing, they were testing the autonomous navigation capabilities of Curiosity rover, and so I was helping with that, and a lot of that involved understanding when it did something screwy, digging deep and being able to explain to people why it did that in that circumstance, and sometimes improving. I also did an interesting sort of internal research project that I led called Science Operations on Planetary Surfaces. So it's maybe not obvious, but the whole purpose of Mars rovers is feeding Mars science. And so the science, somebody equated it to, we're basically bus drivers, and the scientists tell each day, it tells the rover planning team where they want the rover to go that day, and we do our best given the constraints to get the rover there. That led me to lead the sort of the highlight of my career thus far, and probably forever, and that was all of the software and avionics improvements that we made in the Perseverance rover. The Perseverance rover, even though it's got largely the same sort of mechanical speed and vehicle design, drives autonomously 4 or 5 times faster than Curiosity, because we added a little bit of computing, but mainly because we added a whole bunch of smarts and different cameras. And so I led a few different teams associated with that implementation, and then I did for the next year and a half, I did a stint as one of the rover planner teams, the team that, each tactical day looks at the latest downlink image, listens to the scientists about where they want to go, and send up the day's commands to send the robot in the direction that they want. As that ended, I became a group supervisor, so I had a small group where the organizing principle was I had about 8 people that had different flight project leadership positions. So people that led the development of the robotic arm for the orbiter that was supposed to take the samples back from Mars and hand it off to the return vehicle and things like that. And then most recently, a year or 2 ago, I became assistant section manager for the Mobility and Robotic Systems, which is about 140 robotics researchers doing all kinds of super interesting things. And it's a super fun job because I get to dabble and see all of the super cool things that they're working on. I'm going to be quick over this. So I really enjoyed my career at JPL, not just because of the space panache, which I didn't initially sort of value, but came to, but it's got a lot of flexibility in terms of as your interests evolve. It's got a lot of flexibility, so I could work at flight one day and research the other day, and pure software on next project. I'll just talk to the first bullet. So engineering in practice is very much a soft skill. So classwork is all very focused on the science and the math of it, but in reality, very little engineering is a solo endeavor. It is very much a team endeavor, and that aspect of it presents a lot of challenges that they don't teach you about in school. And I'll just say generally, anything that you can do, including an undergraduate, to improve your communication skills, both writing and presentation, you'd be well served. Let's get that. So that's kind of, I'm not that far from retirement now, and since I was all introspective from having made these slides, I had to carry it to the next thing that I might be interested in. Some things I might be interested in doing after I retire. I'll just describe the first one and the last one. So it's really fascinating to see how challenging but powerful it is to get a large group of people talking back and forth about really hard problems. And so I would like to take what I've learned about how that happens. Systems engineering is the general field in development of JPL spacecraft, and apply that to climate change mitigation. So it's a lot of not just the engineering part, but the economics and eventually the politics part of it. So I would like to basically recruit other nerd retirees to figure out what and how to advocate for the solutions that are most effective. In a similar event, I'm just putting an advertisement for an organization that one of my undergrad friends started that basically pairs, mentors with volunteers on various hardware-related humanitarian projects and done some cool things. They did a lot of effort at making ventilators in the early ages of COVID that have since been used in small African villages where not pure ventilators, but just oxygen concentrators. So it seems like a very satisfying endeavor. And that's all I have to say. I was going to show an embarrassing picture of my daughter, but I ran out of time. Anybody have any questions about Mars rovers or engineering college? Yes?
What's your favorite part of one of the workers you built or help create?
Yeah, well, it's got to be the Perseverance updates, and let's see. I'll compare and contrast how the Perseverance software works with how Curiosity works. So it's important to note that Curiosity and Perseverance have super old, super slow processors. So they have 133 megahertz computers. Our gigahertz has got 133 megahertz computers. So it's way less than you have power than you have in your phone. And the way the Curiosity software handles that is it does a very simple evaluation against that terrain map that it made with stereo. It basically is looking at a sphere and is looking at the terrain underneath a sphere, a circle in front of it, and looks at the roughness, and the max fits a plane to it and figures out the top and bottom height. And then it applies a bunch of weights, literally different weights of how much this factor counts versus that factor. And it uses those for all of the different sort of near-term commands that it's considering making. And there's a bunch of heuristics there too that try to keep it from deciding to go left and then to right. So there's just a ton of these sort of parameters whose only justification is when the developer was tuning it, it seemed to make it work better. But it meant that every time something weird happened and it did something that a manager thought it shouldn't, explaining why it did that and not what seems like would have been the easier thing was super hard. So the Perseverance software is a lot cleverer. It actually does a much more refined analysis of what's traversable and what's not. But at the end of the day, the criteria it uses for deciding what to do comes down exactly to how much time does it take to advance n centimeters closer to the goal. So it's super easy to explain once you look at the stereo map why it did what it did. So and I think that's my favorite because I struggled so many times trying to explain, figure out and explain to people what Curiosity was doing. Okay. Anything else? Yeah.
Is there a reason why the computers that you guys use on the rovers are so old? Is it because of power?
Yes, it's power, but it's mainly radiation tolerance. So it turns out as the computers get faster and faster, part of that is that the traces get smaller and smaller, and the component gets smaller and smaller, which in general makes them more susceptible. And this 133 megahertz processor was built in a process specifically to make it relatively robust to radiation. It takes an incredible amount of time to develop and test that. So basically, you only get a new radiation hard processor once every decade or two. And when the project starts, you got to pick the processor that's already existent. And so you end up being like 2 decades behind. And so that's basically it. And I didn't really talk about it, but the new computer that sped things up so much is a field programmable gate array. And so basically it's like a reprogrammable circuit, and they just happen to make a radiation hard version of an FPGA with enough components large enough to support the computation, the vision computation at just the right time for us to be able to demonstrate it and integrate it.
Cool, thank you.
Anybody else? Sure.
How do you think like the industry is gonna change, like with like AI like coming in and stuff?
It's an excellent question. I don't know. There's a tremendous amount of energy behind the application, not of of deep learning in particular, and we're doing it left and right in the reimbursable program. It's been slow uptake in flight because the processes are still slow, and the number of parameters that go into those deep learning models is huge. So there was, for sample return, there was a proposal to use some deep learning techniques to have the arm that's responsible for reaching out and picking up the sample tubes off the ground be learning based. But one of the challenges is that if you decide that what you learned before you launched wasn't good enough and you had to uplink a new model, the models were so large that it would take 4 or 5 days of satellite uplink time to be able to instill a new model. So I think it's coming. And there was an incredible video that I just saw the other day. Somebody managed to make a sort of a deep learning based brain that the same model can control like 15 different robots, and they demonstrated it by disabling a motor on a leg of a four-legged of a quadruped, and the same controller within 15 seconds had adapted and was driving it around. So it's exciting. Okay. Please.
What has made you kind of switch to more climate stuff? Because you said you wanted to pursue that kind of stuff once you're in retirement. What kind of has motivated you to want to do that?
Terrifying news on a daily basis, and it's also, it's a super interesting problem. It's super compelling. It's not really viable to do space stuff, on your own, but mainly, and part of it is my friend Rob, who's been trying to save the world for 3 decades. So he's always been kind of inspiring. So I think that. Sure.
I'm actually interested in majoring in electrical engineering, and I kind of wanted to know about, okay guys, your experience and how you would kind of rate the workload or just anything about it that you would.
Yep. Yeah. So when I was deciding what to do as an undergraduate, I was very explicit that I wanted to do electrical engineering because I wanted it to be tangible. Like I wanted to be able to hold something and see something. And even though my specialty as an undergraduate was signal and systems, so kind of communication, so it wasn't really the seeing things move and such, but I did see enough to recognize that after you put the system together, as a roboticist, a computer scientist gets the same satisfaction of putting something out in the world and seeing definitively how it works in sort of super hard situations. I will say that within robotics, there's a lot of different professions that would all call themselves robotics that have little to do with each other. I mean, there are mechanical engineers, there are electrical engineers, there's software people, there's perception people, there's control people, and they all don't have that much in common, but they all need to come together to make a sort of complicated robotic system. So you'll at some point as an electrical engineer, you will start to sort of be directed to like a digital world or an analog and power world, or when I was an undergraduate, there's probably a different decomposition now, but yeah, I guess that's what I would say, and how I evolved from electrical engineering to computer science. And robotics is super weird because different schools, robotics is centered in some places it's centered in mechanical engineering, and other places electrical. And nowadays it's maybe in all of those doing slightly different things. Sure. All right. Thank you all.
Okay, so for anyone like LCC students who need blocks, sign up on Hello Club, and then we'll make sure you're here.